Hello, and welcome to our short course on models of social dynamics. I'm Paul Smaldino. I'm an assistant professor of cognitive and information sciences at the University of California, Merced. So in this unit, we'll tackle one of what I think is the most important topics in the study of social behavior, cooperation. So let's talk about why cooperation is a problem. Cooperation, first of all, is everywhere. Right? It is the foundation of social life. Multicellular life, when it first emerged, is a kind of cooperation among cells that give up their own reproductive potential to work toward the benefit of the whole organism. We see mutualisms between different species and cooperation between members of the same species. No species more notably than humans, who work together in almost every facet of life. So there are obvious benefits, right, to helping one another and working together. Pretty much all the major transitions in the evolution of life on Earth have involved new cooperative structures, so multicellularity, social animals, language, and symbolic communication. Through cooperation, humans accomplish amazing things. So it's clear that our success as a biological and a cultural species comes from things that we can do together. But it's not obvious how or why cooperation can be sustainable. So if everyone works to benefit others, those that free ride on the work of others get the benefit without paying the cost. So the question is, once present, first, how can cooperation emerge in a population? And then once present, how can it be maintained? So what factors facilitate more or less cooperation? And we're going to look to see how models can help us get some insight into these questions. So a simple model for the principal problem of cooperation is a two-player game called the prisoner's dilemma. Many of you will probably have heard of this. So this is the payoff matrix, this game. It defines the game. The payoffs shown go to the row player. So each player can cooperate or defect. It's non-cooperation. Cooperation incurs a cost, C, on the cooperator and confers a benefit, B, on the recipient, where B is greater than C. This requirement makes the game a positive sum game, so mutual cooperation creates a positive benefit for both parties. Here's the dilemma. Mutual cooperation is better than mutual defection, right? Because B minus C is positive, and so therefore greater than 0. But the best move is always to defect in a single game, because defecting against a cooperator gives you the benefit B without paying the cost C, and defecting against a defector gives you 0, but you avoid paying a cost C and being exploited. So we can reframe the problem of cooperation in terms of this game. How do we get the emergence and maintenance of cooperation in a population of individuals playing the prisoner's dilemma? To answer this question, we need to talk a little bit about the dynamics of how strategies will change in a population. And to do this, we're going to talk a little bit about evolution. So there are 3 requirements for evolution by natural selection, which is what our analysis would be based on. Evolution by natural selection requires 3 things. 1, there must be variation. 2, that variation has to have consequences for survival or reproduction. There must be something for selection to act on. And 3, that variation must be heritable. So here we'll assume that individuals use behavioral strategies related to how they play the prisoner's dilemma game, meaning that there's fitness consequences, and that those strategies vary both between individuals, so variation, and are heritable. I think it's fairly clear that if there are multiple strategies, there's variation, but it's worth saying a little bit more about selection and heritability. So transmission of traits from one organism to another can occur via a number of mechanisms, including both genes, which is what we often think of when we think about evolution, or through social transmission, that is, by learning. There are other ways, including inheritance of environmental constraints on development, but I'm not going to discuss these here. In the case of human cultural traits, we are often talking about social transmission. Luckily, several transmission mechanisms are roughly equivalent in our model. So, if individuals copy their parents, then the individuals who have the most offspring will propagate their traits as if they were genetically determined. So this is something called vertical transmission, and this sort of vertical transmission of social information can include active teaching as well as less conscious processes. Like you just happen to be in a certain environment that is related to what your parents are like. Alternatively, consider the case where individuals actively assess which individuals to learn from. Right? They look around and they see, well, certain behaviors lead to the accumulation of desirable resources, and if individuals can assess differences in resources and imitate the strategies of successful individuals, then again, the most successful traits will propagate in the population. So this is called success-biased transmission. And what's nice is, in any case, in all of these cases, the dynamics of the model work out the same. Successful individuals will preferentially transmit their strategies. So, let's talk about a simple prisoner's dilemma game model. So just like in the previous unit, we'll use a square lattice structure in which agents interact with their 4 nearest neighbors. We'll start by assuming that agents play pure strategies. That is, an agent is either a cooperator who always cooperates or a defector who always defects. Each time step, every agent will play a prisoner's dilemma game with each of their 4 neighbors and accumulate a payoff. Then we have evolution. Every agent will consider their own payoff and the payoff of all of their neighbors. If any of the neighbors have a higher payoff than they do, the agent adopts the strategy of the neighbor with the highest payoff. That's basically it. That's the entire model. It's a very simple model, so I want to talk a little bit about simplicity. Right? The model has a very simplistic view of both social behavior, structure, and evolution, be it cultural or genetic. So starting with simple models is a good thing. Simple models give us a place to start, and in general, it's good to remember this about modeling. Right? The baseline model will often be extremely, stupidly simplistic. But simple models can give us insight, including insight into the sort of additional complexity we might or might not need to make sense of our systems, as long as we don't forget that we've made those critical simplifications. And I hope this course continues to demonstrate it's not always obvious how an apparently simple system will behave. So, okay, let's get to the model. Before we get to the code, let's talk briefly about payoffs. Right? So remember, in our model, an agent is going to have 4 neighbors. So to calculate payoffs, right, an agent considers all of its neighbors, so n neighbors, but in this case n always equals 4, of which n sub c are cooperators and n sub d are defectors, where n sub d plus n sub c is n. Right? So to calculate the payoff to a cooperator, v is often used to calculate to designate payoffs. It's just the number of cooperators times the benefit, the payoff to cooperating with a cooperator, minus the number of defectors times the cost of interacting with a defector. And we can, because n sub c plus n sub d equals n, right, we can simplify it this way. Right? It's the number of cooperators times the benefit of cooperation minus the cost of cooperating with everyone. Payoff to a defector is calculated similarly, but it's just the number of cooperators times the benefit of receiving cooperation. Right? Defectors pay no costs. They just let cooperators cooperate with them. So comparing these, something becomes very obvious. Right? It looks like the payoff to a defector is always greater than the payoff to a cooperator. One thing to remember is n sub c doesn't have to be the same for everyone. So cooperators can potentially do better in the model, but only when they can interact with more cooperators than defectors can to offset the cost of cooperating. So let's look at our model to get some more intuition for how this works. Okay. So start out with PD underscore simple dot and logo. Go to our code. Here it is. We have 3 sliders. One for the initial frequency of cooperators, or how many individuals are cooperators. The benefit of receiving cooperation, which I'll just leave at 1 always because the ratio between B and C is really what matters, and the payoff cost. I've noticed I've also had both a regular go button, which goes forever, but also a go once button. I've done this just by having it run the command go, but unchecking forever. So it just runs go once. And this allows us to examine in a little more detail what happens on each time step. Okay. Looking at the code, agents keep track of what their strategy is. So 0 for defector, 1 for cooperator, and their payoff. In setup, we just create all the agents. Just like before, every patch will sprout an agent. And then with probability init coop frequency, that agent will be either a defector or a cooperator. And then agents are recolored so that cooperators are blue and defectors are red. Let's go to the dynamics. First, if all of the turtles, all of the agents are either all defectors or all cooperators, the model stops running. Then all the agents play the game and accumulate payoffs. Then they all evolve. They all imitate the strategy of their best performing neighbor, and then they all recolor. So first, each turtle will reset its payoff, count the number of neighbors that are cooperators, count the number of neighbors that are defectors, and then if the agent is a cooperator, it calculates the payoff to a cooperator based on those neighbors. If the agent is a defector, it does the same. Every agent does this. So then, when it evolves, every turtle will look at the neighbor with the highest payoff, and if that payoff is greater than its own payoff, it adopts the strategy of its highest performing neighbor. And that's it. That's the whole model. So here, let's start out with what happens if most individuals are defectors. So only 5% of agents are cooperators here. And I'm plotting here the frequency of cooperators in the population. Go once. Up, everyone became a defector. So cooperators don't do very well when they're extremely rare because they can't find enough other cooperators to interact with. What if half the population are cooperators? Well, looky there. Cooperation does extremely well. And this is maybe surprising, right? Cooperators dominate. So maybe this isn't such a dilemma after all. What's going on? Let's look at this case a little bit more carefully. So notice in the time course of a run, the frequency of cooperators first goes down and then up. Right? So defectors increase rapidly when cooperators are scattered. So I'm going to show you what I've done is taken screenshots of every time step here for the first 8 steps of a model run. And so here you see, here's our initialization in this first one. And in the first time step, the number of cooperators goes way down. Defectors exploit cooperators nearby. They do better than their cooperative neighbors who are being exploited, and defection spreads. But in some regions, just by chance, there's enough cooperators that cooperation persists. Cooperators are cooperating with enough of their neighbors to outperform their defecting neighbors. And these clusters do quite well because mutual cooperation, if you can cooperate with enough other cooperators, can therefore spread, and it spreads quite a bit until we just get these kinds of little ribbons of defection where defectors can exploit, a few defectors can exploit a kind of big sea of cooperation. So let's look at this. Let's go back to our simulation and see what happens when we increase the payoff. Again, here's 0.24. We see the same thing happens. Cooperation spreads. Let's just increase it to 0.25. Should be the same. Nope, not at all the same. Right? Affection is doing very well. Cooperators are barely hanging on, just these little islands of lots of cooperation, until once I get to payoff cost of 0.5, affection completely takes over. So what's going on here, right? Well, first, let's just take a look at this in a little more detail, right? I talked about the fact that a little bit that running the simulations one at a time, getting a sense of the model dynamics with visualizations and just paying attention to individual runs is really valuable for getting intuition. But when we want to characterize the behavior of the model as a whole, we want to run lots of simulations over lots of parameters. So here, I've run 10 simulations for 100 time steps for each value of C, of the cost of cooperation, between 0.01 and 0.5 in increments of 0.01. So the dots are the individual runs and the line are the averages. And we see that cooperation does really well, right up until C equals 0.25, just as we said. So cooperation here plummets, and then cooperation does not very well, but sticks around right up until 0.5, and then it just goes to 0 every time. So there seems to be these thresholds. So what's going on? It's useful sometimes then when you see things like this happen in a model to dive in deep and think about how exactly the model works. So let's zoom in here on a case where there is a trio of cooperators. So if there's just two cooperators, cooperation is never going to survive in this model, because each cooperator is only cooperating with one other cooperator, and cooperating with one cooperator is never as good as defecting against one cooperator. So that's never going to work. So the minimal case is two cooperators. There's a cooperator cooperating with two other cooperators, so a row of three. So here's this case. Now imagine that next to these three cooperators is a defector. What's going to happen to this defector? What's it going to do? So a nearby defector who interacts with one cooperator has a payoff of B. This cooperator who cooperates with two other cooperators has a payoff of 2B minus 4C. Always 4C, because it's always paying the cost of interacting with four people, four agents, and it's getting the benefit from two of them. So cooperation spreads when 2B minus 4C, the payoff to that cooperative neighbor, is greater than the payoff to its defector neighbor, B. And if we do a little bit of algebra, we can rewrite this as C less than B over 4. Since B is always 1 in our simulation, this occurs when C is less than 0.25. So as soon as, if C is less than 0.25, cooperation can spread. When C is greater than 0.25, it doesn't. This case does not spread. So when C is above this threshold, cooperation declines, but we saw it doesn't vanish entirely. Some cooperators usually stick around as long as C was less than 0.5 or less than B over 2, right, because B is 1. But above that threshold, cooperation goes to 0 always. Why? So in our model, a cooperator can receive at most 4 acts of mutual cooperation if all of its neighbors are cooperators. So let's look at when even this is not enough. So let's consider a single unit of 4 cooperators. So that cooperator in the middle is getting, is paying the cost of cooperating with 4 agents and is getting the benefit of cooperation B from all 4 of them. So that center cooperator gets a payoff of 4B minus 4C. A nearby defector can interact with 2 of these cooperators. So it can get a payoff of 2B. So this cooperator formation is stable as long as 4b minus 4c is greater than 2b. Or if we do a little algebra to rewrite this, it's when c is greater than b over 2. So as soon as that's the case, so as soon as c is greater than b over 2, cooperation disappears because that question mark cooperator will switch to defection. Okay. So let's talk about cooperation and assortment. Right? Cooperators can do really well if the cost isn't too high relative to the benefit and if there's sufficient ability for them to assort. Right? We can see there are limits to this if we consider invasion of just a few scattered cooperators. Like we saw that even with a good payoff matrix, if there was just 5% cooperators, there wasn't enough initial assortment for cooperation to persist. In general, this assumption of assortment is a very strong one. Right? We've assumed that social networks are very rigid, never change. That your neighbors the agents who are your neighbors now are your agents or your neighbors forever, or that their offspring are your neighbors, your offspring's neighbors, etc. Right? So let's challenge this assumption with a very simple extension to our model. And we'll do this by doing a little randomization. So in our first model, agents interacted with neighbors in a fixed network structure. Right? Neighbors at the start are your neighbors forever. But now let's introduce probabilistic randomization. So every time step, every agent has a probability of switching its spatial position with a randomly selected other agent. And this will disrupt the spatial assortment that can emerge that we saw before. So let's look at how just a little of this, just occasional randomization, changes cooperation. So let's look at the code PD underscore randomized. Got that logo. Pull up our code here. So you see we've added a new slider called randomization prob. Let's look at how this is implemented. So everything is the same as before, except in the dynamics, right, before playing the game, we have a new procedure called randomized location. And this just makes agents move around to reduce assortment. So here's how it works, right? All the turtles, just with a probability randomization prob, they look at their current position, and then they choose another agent at random, and they swap positions. And that's it. And then they play the game. So their neighbors at one time will be uncorrelated with their neighbors at another time. So a little of this, if randomization prob is low, then most of the assortment, most of the network structure is going to be preserved from one time to another, but it'll be a little bit disrupted. And then the higher the randomization prob is, the more disrupted it'll be. So let's look at what happens here. Here's with no randomization. Again, we see lots of cooperation persist, and it's doing really well. Now we've had a little bit, just 1% randomization. You see, first of all, the situation is more dynamic, but cooperation's doing okay. It took a little bit of a hit, not a huge amount. And to make it 2%, it starts oscillating a bit more. 3%, more oscillations, and kind of a downward trend is emerging. Let's make it 4%, 5%, 6%, 7%. And the cooperation, sometimes it goes back up, but it's not doing so well, right? Cooperation is not persisting so well. 8%, cooperators are barely hanging on. And 9%, they're really in trouble. And 10%, that's the end. Right? No more cooperation. So again, let's look at this in a little bit more detail. What I've done is run 20 simulations for each value of randomization prob between 0 and zero point 0.1 in increments of 0.05, or 0.005 rather. And what we see is that with only a little bit of randomization, cooperation suffers a lot. And past a certain point, so here at 0.9, 0.09, 9% randomization, most of the runs go to 0 eventually. A few hang on at 200 time steps, and by 0.1 they all go to 0. So when it comes to thinking about cooperation, this is a problem, right? Because our assumption of strong assortment is not going to hold for many real-world cases, right? Cooperative partnerships cannot be fully exclusive a lot of the time, especially in the case of humans. We interact with lots of people, many of whom could easily take advantage of us if we're just naively altruistic, giving our time and resources to anyone we meet. So to recap, naive cooperation can invade and be maintained in the population if the costs of cooperation aren't too high and there's enough strong assortment across generations and enough initial cooperators for some assortment. But these conditions are not likely to be met often, especially for humans who interact with a wide range of other people. So let's consider a scenario where there is an opportunity for cooperators to be a little bit more savvy. And this is a scenario called the Iterated Prisoner's Dilemma game. And it's based on the idea that what if interactions, instead of happening once, last for a while? Right? So previously we assumed that cooperative interactions just occurred once per time step, and then everyone interacted with their neighbors once, and then they copied their best performing neighbor. So this is fine if we're considering pure strategies, since the performance of a pure strategy in one round of gameplay will be the same as in many relative to others. But what if interactions between players don't occur just once, but several times, and we consider contingent strategies in which individuals have the opportunity to update their behavior based on what happened in the previous rounds? So our game has shifted to the Iterated Prisoner's Dilemma game. And this just means that pairs of players play multiple rounds of the Prisoner's Dilemma game. And we'll introduce a new contingent strategy, Tit-For-Tat. So Tit-For-Tat is a strategy that is cooperative but responsive. It is following a principle of reciprocity. Tit-For-Tat doesn't like being exploited. Tit-For-Tat starts out cooperating, just like pure cooperators, but thereafter it copies its co-player's last move. So it will happily continue to cooperate against another cooperator, but will only cooperate with the defector once, unless somehow the defector also switches tactics and starts to cooperate. And many studies have considered lots and lots of other kinds of contingent strategies. For now, we're just going to think about Tit-For-Tat. Okay, so here's where the importance of the iterated game comes into play. If we only play once, then Tit-For-Tat doesn't do any better than a pure cooperator, since by the time it's ready to respond, the game is over. But when the same pairing has multiple opportunities to cooperate, Tit-For-Tat is only exploited once, and thereafter it prefers mutual defection to being played for a sucker. So we're going to need to update our model to account for multiple rounds of gameplay, but we can do this pretty easily. Let's look at how Tit-For-Tat fares. First, let's just take a closer look at the payoff. So imagine a game that lasts for X iterations. Right? Here we look at the payoffs for each strategy against another player using any other strategy. So both cooperators and Tit-For-Tat do badly against the defector. So defectors against another defector get 0, but both cooperators and Tit-For-Tat agents get negative payoffs, so they do worse. But cooperators do a lot worse than Tit-For-Tat because they get exploited on every round, and Tit-For-Tat only gets exploited once. Against a pure cooperator, defectors do better than either pure cooperators or Tit-For-Tat again, because they just continuously exploit them. And cooperators just get mutual cooperation, as do Tit-For-Tat agents. So it looks like defectors are going to do better than cooperators, But now let's introduce Tit-For-Tat. Against Tit-For-Tat, defectors can only successfully exploit once, whereas Tit-For-Tat and cooperative strategies can still reap the benefits of mutual cooperation for all the iterations. So look at this closely. Against a cooperator, a defector gets X times B. It gets the benefit for every round of interaction, but against a Tit-For-Tat agent, it only gets the benefit once. So this helps us maybe get the intuition that if the interaction goes on long enough, Tit-For-Tat can maybe outperform defectors. Let's consider our payoff calculations. Right? I'm going to consider a spatial world of just defectors and Tit-For-Tat. So everyone is either Tit-For-Tat savvy cooperator or a defector. Now, we're going to see something interesting. So just as before, an agent considers n neighbors, or n is four neighbors, of which n sub t are Tit-For-Tat and n sub d are defectors. The payoff to a Tit-For-Tat agent after x iterations is x times n sub t times b minus t minus n sub d times c. So this is the payoff for mutual cooperation times x iterations minus the cost of cooperating against a defector, but it only pays that cost once, not x times. Payoff to a defector is the number of Tit-For-Tat agents times b. Notice x does not appear in this because it only gets this benefit once. So even though Tit-For-Tat is paying a cost, if x is large enough, it might be able to outperform defectors as long as it can interact with at least one cooperative neighbor. It doesn't actually need more. So pure cooperators, we saw, needed to interact with more cooperators than defectors did. So they needed assortment. Tit-For-Tat doesn't necessarily need more assortment as long as the game goes on long enough. So let's take a look at this. We can add this to our model. The code will be pd_reciprocity.nlogo. Take a look. All right, what I've done, I've added a switch here, on-off TFT, and that when this is off, the game is played just as before with pure cooperators, and when it's on, all the cooperators will be Tit-For-Tat agents, which will be represented in green. Here's our randomization prob, and here is another slider for the number of iterations. So we have to update a little bit with the code, so recolor, this makes the Tit-For-Tat agents green. And then our calculations of payoffs have to take into account the number of iterations. And we write these equations just as I wrote in the previous slide. Okay. Other than that, everything is exactly the same. So let's see what happens when we start introducing some Tit-For-Tat. First, let's notice that if the number of iterations are 1, the results are going to be exactly the same. So if the payoff is 0.21, so that's less than 0.25. Sorry, randomization is 0. Good spatial assortment, everything is great. Goes up, not so good. Pass 0.5. Cooperation goes to 0. Now, let's increase the number of iterations. Let's say, 4 iterations. Now, the payoff cost here is 0.5, so cooperators did terribly here. This is where cooperation just went to 0. Let's look at Tit-For-Tat. Tit-For-Tat doesn't just hang around, but it totally dominates. And this, we can do this, let's make the cost 0.6. Yeah, still killing it. All right, well, so far we're assuming very strong assortment again, so cooperative clusters can persist. So let's turn the randomization prop all the way up to 1, right? So no more assortment at all. All interactions are totally randomized. There's no correlation between one time step and another. All right, Tit-For-Tat didn't do so well this time. Yeah, not doing so great. Oh wait, let's make a few more initial Tit-For-Tat agents. Look at that. So at this point, not so easy for them to grow in number when they're rare. But if they're common, Tit-For-Tat can do well even with very high payoffs, very high costs to cooperation. Let's look at the case where C cost is 0.3. And there's very few initial Tit-For-Tat agents, just 5% again. Okay. And let's add a little randomization, but some assortment. So 0.1. So under these conditions, pure cooperators are going to get trounced. Right? Know this. Not Tit-For-Tat though. Tit-For-Tat does exceedingly well, right? Because even though Tit-For-Tat agents rarely find each other initially, as long as they do it occasionally, the benefits of their repeated interactions can still outweigh the costs of being exploited. So in general, a couple things are worth noting. Tit-For-Tat is a lot more robust than pure cooperation. It can permit the persistence of cooperation under greater costs and lower assortment as long as interactions persist long enough so that there's ample opportunity for reciprocal cooperation. It's okay to be exploited if you can subsequently ignore exploiters but continue to interact with other savvy cooperators. So this is actually a general principle that of cooperation, of reciprocity, and the evolution of reciprocal cooperation or reciprocal altruism is a massive topic of research. So let's talk further directions. There is a vast amount of work modeling cooperation, much of it focusing on solving the prisoner's dilemma. There's also a lot of empirical work, both in humans and non-human animals. In general, it's a very rich literature. The research on cooperation and assortment that the first part of this lesson is based on originally dates to W.D. Hamilton's work in the 1960s. Hamilton discussed genetic relatedness as an important mechanism for assortment. The work on reciprocity stems from two seminal papers, one by Robert Trivers in the early 1970s and the other by Robert Axelrod, and W.D. Hamilton in 1981. A lot of research on cooperation explores various mechanisms for assortment, which also includes work on group structure, network structure, movement strategies, environmental harshness, and reputation management. So cooperating with those who have a reputation for cooperating is sometimes called indirect reciprocity. Cooperation in larger groups. Our model focused on cooperation between two individuals, but cooperation sometimes involves larger groups. A related game called the Public Goods game is a sort of in-person prisoner's dilemma game for arbitrarily large groups. When cooperation involves groups of more than two people, it turns out that reciprocity doesn't actually work that well as a strategy, partly because defectors can free ride on the efforts of the majority. You have to think, what if a few people in the group don't cooperate? Do you then stop cooperating even though the rest of the group are still cooperating? This kind of thing requires something more than just reciprocity. Uh, and this fact may be one of the reasons that altruistic behavior is rarely observed in large, unrelated groups of non-human animals. To get cooperation in large groups, we need something else. Analyses of the public goods game have considered a number of important psychological and institutional mechanisms like conformity, reputation, punishment, and policing. Cooperation and competition. So there are many other issues relevant to cooperation other than simply avoiding or punishing free riders. Group boundaries and markers can help identify individuals, identify certain other individuals to cooperate with or to avoid, for better or worse. Cooperation is also part and parcel with intergroup conflict. Right? Intergroup conflict is a kind of cooperation between members of the group cooperating in the act of conflict. And there is a lot of literature suggesting that conflict may actually drive cooperation, as more cooperative groups will be better able to compete. Because cooperation is such a core part of human societies, there are really many important avenues for research, including many untapped or rarely explored ones. So that's all I'll say about cooperation for now. Up next, we'll talk about coordination and norms. Thanks for watching.